Hi, my name is Amy Little, and I've done my research project on named data networking, a TCP/IP solution. The internet has changed a lot since its inception in the late 1980s. How we use it has changed as well as why we use it. Originally, it was intended as a point-to-point system, so emails or chatting were very common. But as things have changed, multicast uses have taken precedence. So Netflix, Hulu, YouTube, or Facebook have become popular. With the previous TCP/IP architecture, the point-to-point system made sense, but now that things have changed, issues are arising as a result. And NDN, or Named Data Networking, seeks to solve some of these issues. Named data networking works by creating two packets, the interest packet and the data packet. The interest packet is created at the beginning and it has three sections: the content name, the selector, and the nonce. The content name is arguably the most important part of the interest packet and data packet. This is the part that replaces the IP address identifier that is currently used in datagrams with TCP/IP. So before, where you'd have to identify the IP address of the sending and receiving nodes in order to make a connection, now with NDN, you would be able to use an identifier. For example, if you were looking for Google News, news.google.com, the identifier would be com/Google/news. So this is a huge shift, as you can tell. The selector is an optional field with a preference or scope, and then the nonce is a random number that is assigned by the pending interest table in the routing scope. And I'm going to go into these a little bit more thoroughly as we go through the presentation. Once the interest packet has been created, it follows a specific path through certain sections in a previously configured router. And those are three sections. The first one is the content store, or CS, the pending interest table, PIT, or the forwarding information base, FIB. The content store is the first stop for the interest packet. And this is where you're going to find interest packets that have been previously fulfilled. So once the interest packet has gone through this routing path, has been discovered and followed back, it's going to be stored here. You would find commonly visited websites cached here. For example, if you visit google.com often, it would be sent back and stored here, so the next time that you're searching for it, it would be easy to bring back up. So if it's not found in the content store, then the interest packet goes to the pending interest table. And the pending interest table is where interest packets that have no data packets returned are stored. So again, if you've sent out a packet for google.com but it has not yet been returned, you're going to find it in the pending interest table. This is also where you're going to find that nonce, or random identifier, is assigned. And I will go into that a little more thoroughly a little bit later. And following the pending interest table, you're going to see the forwarding information base, or FIB. And this is a routing protocol very similar to the one currently used with TCP/IP, and it is the final step before the information is sent out to the web. So once the information has been sent out to the web and it has been returned, it is returned in the form of a data packet. The data packet has four distinct sections. The first is the content name, which contains the object identifier. This will be the same identifier that is identified in the interest packet. So if we had previously sent out the interest packet with com/Google/news, the same identifier will be on the data packet. Next is the signature, which is the signature of a producer available for review, and then the publisher key that is required by the responding node, and finally the data portion, or the website that you were searching for. And these follow the routing protocol in reverse. So it basically goes back from the forwarding information base to the pending interest table to the content store, then back to the requesting node. There are a number of ways in which named data networking addresses the various security and networking issues in the TCP/IP architecture, and I've chosen just a few of these to illustrate how named data networking works. The first one of these is the sequence number attack. So TCP is a connection-based protocol, meaning that the nodes must have an established connection in order to transmit data. This can be known as a three-way handshake, and how that works is that the authenticating device, or node A, sends an SYN, or synchronization packet, to node B to establish the connection. Once the connection is viable, node B will send back an SYN ACK, or synchronization acknowledgement packet, containing ISN, which is initial sequence number information, as well as IP information for both nodes. Once this has been received from the authenticating node, The final ACK or acknowledgement packet is sent, again, with the originating ISN number and the IP address information. Now, in this process, how a sequence number attack would work would be if a third party was monitoring these packets being sent back and forth and then uses that information to ID the ISN and the IP address information. Once it knows this, it can issue false packets into the process that act like the genuine packets of the original source, node A, and using that they can gain access to one or both of the nodes. Now, the NDN solution to this is obvious. There is no IP address information required in order to gain access to content. The three-way handshake is not required in NDN because it's not a connection-based protocol. But the more interesting part of this is that even if an interest and data packet were intercepted by a third party, there is no identifying information contained. It's just the object identifier or the thing that you were looking for. And this can create a whole new level of security in this situation. Another instance in which named data networking addresses security issues associated with TCP/IP architecture is the case of DNS server attacks. DNS servers have caches containing IP addresses associated with host names, operating system and configuration information, amongst other things. DNS spoofing, which is one of these attacks, occurs when IP addresses associated with trusted sites are replaced with third-party sources. This diverts traffic to the third-party computer. For example, if you frequently visit a website, say google.com, and a third party has diverted that IP address, the next time you access the site, they can gain access to your system. Obviously, this can lead to many issues, including viruses and data loss and memory loss. The NDN solution to this is actually quite clever. It's contained in the signature key that's on the data packet that's returned with the content. This is a signature that is required by the source of the content, as well as a publisher public key digest and a signature algorithm. This can be viewed to verify the validity of the source. So for example, if you were to visit your bank's website, say www.bank.com, and you were led to log in using your account information or username or password, if you were diverted to a third-party page, you could give them access to that information without even knowing it. In the case of NDN, you would be able to verify via the data packet that this is actually the bank.com website that you were diverted to. So you can imagine it's quite a useful discovery. Now, routing is another area where there can be issues with TCP/IP. And there's a great solution to this through NDN. So a routing protocol might be that node A wants to route information to node C, and it would need to do this by going through node B. So node A sends the information to node B sends the information to node C, and then the information is routed back to node A, establishing the connection. So this was great, and it is a functional routing protocol. Now, routing a loop occurs when node C goes down for any number of reasons, and then the information that is sent from node C to node A is lost, the information from node B to node C is lost, and when node B sends information to node C, it's kicked back up to node A, the originator. And node A recognizes it as something that needs still to be fulfilled, so it sends it back down to node C, and it does this in an endless loop, leading to bandwidth issues, sometimes network crashes, and security issues. It can be a big problem if it occurs. The named data networking solution to this is also in the signature part of the data packet. Instead of being in the publisher ID, it's in the digest algorithm, which is where the nonce is located. So, for example, when the interest packet is sent out, it's assigned a random nonce by the pending interest table. When the data packet is returned, it will have the matching nonce. So if we sent out a data packet, the interest packet with com/google/news, it might have \123 is its identifier. When the data packet is returned, in its content name, it'll say com/google/news\123. Now, when it's returned, the PIT or pending interest table cross-references the nonce on the data packet with the nonce that was originally on the interest packet to determine if it matches. If it matches, the interest packet is discarded and the data packet is passed back through the routing protocol and back to the user. Now, say an interest packet is returned instead of a data packet, and so there's an interest packet already in the pending interest table that matches the one that's being returned. The pending interest table simply disregards or discards the second interest packet and waits for the data packet to be returned. This prevents those routing loops from occurring. Another interesting section of this is that since interest and data packets are focused on objects over source and destination information, there's more bandwidth available for searching, so you don't run into those bandwidth loss issues. As well as, with the threat of routing loops being lifted, the router is then free to explore alternate routes for the packets to follow in the case of network issues. So if an interest packet goes out and it's encountering issues at different routers, it simply just continues to look for other paths. And this is it would be a huge change for the way things already are working. As you can tell, named data networking is an interesting prospect for the future of the internet, but it is very new. It was only first presented in 2006 as content-centric networking, which is its father architecture. The first NDN community meeting took place this year in September, a few months ago. Professionals from all over came to UCLA to discuss the various aspects of development and implementation. Of course, a shift this large has many components, so it's difficult to implement on a very wide scale, but the community is growing all the time, so it's gaining a lot of steam. In other words, you may start hearing more about this in the years to come, and that makes it a very exciting project to work on. If you're looking for more information on named data networking, you can go to www.named-data.net. This is sort of a website that is the collective effort of the international community working on this project. So you'll find exciting TED Talks, publications, and progress summaries, sort of everything that everyone is working on at this time. The reason I chose named data networking for my presentation was that it's sort of an exciting, cutting edge thing. It could be the next evolutionary step of the internet as we know it. And for that reason, it's important to be aware of it and to know as much about it as possible. Thank you very much.